the discussion on pneumatic elements, pneumatic measurement systems. The pneumatic measurement system is in practice quite long. There are certain advantages of using pneumatic measurement system and also pneumatic actuators. The major advantage is that it does not need any electrical signal. So that is a major advantage. One major advantage is non-usage of electrical signals. Though electrical signal transmission has a lot of flexibility and it can be modulated easily, and the whole instrumentation, measurement and all systems are radically changed because of the usage of electrical signals and systems. However, there is one disadvantage of electrical signals, especially little bit of high current signal, is that uh, if there is some kind of loose connections or loose contact, then there can be a sparking, and in some environment, the electrical sparks can create havoc. So therefore, this pneumatic measurement system can be used in such hazardous or explosive environments. Pneumatic measurement and actuating system was devised long back along with the mechanical measurement and actuation systems in the 18th centuries and then in 19th century as well. However, it went down to 20th century, and even now also pneumatic actuators are used. It has the second advantage is that it can carry more pressure or more power. It can exert or it has another advantage of high weight to power ratio, high power to weight ratio. So that means if you have a motor-based, electrical motor-based actuators, so which is used to drive certain actuation, so the weight of that motor is usually higher than its hydraulic counterpart. So if I use a hydraulic or pneumatic motor, the power carried or exerted, force exerted by that actuator is more for the same weight ratio. So this is the second advantage. But it has also a lot of disadvantage. Major disadvantage is leakage. and maintenance. So leakage is a perennial problem for hydraulic component, but it is uh, also present in case of other pneumatic systems like gas-based systems. There also leakage is a problem, but it's a big problem in case of hydraulic, where either oil or water is used as a transmitter. Mostly oil is used as the transmitting medium, because water is conducting. So during interface and side by side, if there are some low voltage electrical wires are running, so leakage can create problem. So that's why oil is used. Also, oil has this high pressure ratio is more for oil. So these are the some things about the pneumatic system. So here the signal, as you all know, that the pressure is a signal. So pressure and the volume uh, of displacement. So these two are basically the output or the signal.
Sir,
Yes.
sir, just now you said something, some ratio for oil is high. Sir, what ratio?
So that means if I have a hydraulic motor is like, say, I have a water jet, water pipe, and that water pipe or oil pipe, and on the oil pipe I have put some fins, okay. Then those fins will be driven by the pressure of this hydraulic jet, and then it will rotate, and corresponding to that we can do the various functions. Like I can make have a linear actuations by having a piston based actuation. That means the water will push the piston in a linear manner in x direction, back and forth. Okay, so that will generate a certain power. Now, if that same thing is implemented using electrical motors, that I have to do the same task, like I have to move 1 ton of, say, certain weight from a position x0 to position x1. Okay, so then, that platform need to be moved. Now, with a reduced size hydraulic actuation, we can that uh, move that weight from position x0 to x1. So that means same size of hydraulic actuation devices will produce more power or more force, final force. Okay. So this can be, you might have seen hydraulic compaction. Okay. So they are also that used that same principles. If we use a small jet is there, okay, through a narrow port, and then a piston is connected to a wider port, so that way the force amplification takes place, and then in that below that piston the compaction will take place. So all such thing, performing such thing, hydraulic components have this power to weight ratio, better power to weight ratio. That means within the same size, you can generate more force. Okay. Is it clear?
Yes, sir, I understood now. Thank you, sir.
Now, so we shall discuss today about a system for displacement sensing, because basically we are discussing measurement, pneumatic measurement system. So this part is there in Bentley. This can be used as feedback as well. So this is called clapper nozzle displacement sensing system. So in our instrumentation lab, we had a pneumatic system, but unfortunately now there is some problem of leakage. It is giving some trouble. So basically, there is a pressure port through which some oil, water or gas is driven, and here is a programmable orifice which can be, this constriction can be programmed, and from this side we have the supply pressure. Correspondingly, there will be a mass flow, and sorry, I have a, then there is an output port. Here the flow rate is m dot, and we have output P pressure, P, and correspondingly we will have a volume. And volume V. So this is a, you can think of as a reservoir. Now here therefore mass flow will change. Mn dot. So this is a narrow output through which air or gas is coming out. Then at this place we have a small plate. So it can be hinged in one side, then the displacement will be nonlinear. Okay, if I hinge it on one side. For simplicity, we can take it linear displacement. Generally, in the experiment in the lab, this has been hinged. to this side. So this is a small thickness plate which is flexible. If it is hinged this side, then it is flexible. If it is not hinged, like has been connected through some lever both the sides, and then with this pressure the whole thing will move through a roller. So then that is, so this is called a flapper. Now the purpose is to measure the displacement of this. So basically this flapper is connected to a moving object. In case of lab, of course, there are screws are there. I mean, we can move it physically, or otherwise, a flexible flapper is provided for the experiment, which has a displacement uh, corresponding to a cantilever. So through that nozzle, actually, the gas will come out and it will create a pressure, and that that will be fed back to this. Depending on, because it is a nozzle, so there will be, the gas will move like this, and depending on the area of the exposure, actually the mass flow rate and the pressure, back pressure will be controlled. So now if we equate the mass flow in the pipe, we have,
Sir,
yes,
sir, could you please repeat that part of what is happening, like back pressure, that one?
actually mass flow rate will be controlled depending on this, depending on the vicinity of the flapper, and also pressure will be controlled. So here, if it is freely moving, then of course there is no back pressure. We can, to simplify, we can put this is atmospheric pressure. As the reference. So the pressure that will be transmitted to this output port will depend on this mass flow Mn. Okay, so that can be found out from this. We have m dot which is going to this output is equal to m o dot minus mn dot. Okay, so that is simply continuity of the mass flow. So we have assumed that this is not compressive, then only this, of course mass flow can be there, but in the pressure and mass flow, those relation with volume we can put next. So m dot m can be, we can first put m. So mass m is weight into volume, and of course, we can use that relation PV equal to n r theta, so divided by r theta into P. Assuming ideal gas. Where n is the moles of an ideal gas, n is the moles. And that it is mass divided by molecular weight. And if we put in kg, usually moles are mass in gram. So if it is kg, I mean kg into 1000 divided by molecular weight. So then, of course, if it is MK system, then in mass is in kg. Then mass m, if it is in kg, this should be divided by r theta. So this should be here 1000 will come into 1000 into P. So mass flow rate would be so this is simply dm dt Wv by 1000 r theta assuming that volume does not change. So therefore we have put this as constant dp dt, and there is also no leakage, so that is also assumed. So this is the, if we get the m dot, this is m dot, then mo dot is mo dot, actually you might have studied orifice. You have studied orifice in instrumentation devices 1. So by we are restricting this area through an orifice, okay, we can do it also like venturi, etc. But correspondingly, whatever restriction element we use, the discharge will be controlled corresponding to a formula given by that particular mass flow controller. So like if it is orifice, then mass flow rate in orifice is given corresponding to the differential pressure at the supply pressure side and this output pressure side. Okay, supply pressure is PS and the output pressure is say P. Okay, so here we have P, here we have PS. So the differential pressure, will determine the mass flow rate. So MO rate from the relation of mass flow rate with differential pressure across orifice. So that will be given whatever the formula we use, and for the orifice we have, there are many formulas. One of them is discharge coefficient multiplied by pi by 4 d0 square is the diameter of the constrictor, and it is square root of that pressure 2 rho, then the differential pressure term PS minus P1. If the density remains same, rho will come outside. It will be square root of root 2 will also come outside. So it is square root of delta P. So that way we know that the mass flow is non-linearly related with the orifice. Okay, I think this is being recorded. So similarly, the mass flow rate Mn hat will be again related by the, I think, okay, I can call it Cn or Cdn. This is CDO, discharge coefficient of the orifice. This is CDN, is the discharge coefficient of the nozzle. Nozzle usually instead of this pi by 4 d0 square, here it is pi dn, the diameter of the nozzle, into x, the distance is also comes into picture, and similar to that we have 2 rho. Here we have P is the input and atmospheric pressure is the PA is the output. So if we assume to be gauge pressure, no, first let us make it mass balance at steady state. Where this reservoir output dashboard reservoir, that side or that is all consumed. So dp dt equal to 0, giving m dot equal to 0. So that means towards that output where the pressure is now steady, so dp dt would be 0 and giving m dot equal to 0. So then we have the output mass flow rate through the orifice equal to the mass flow rate in the nozzle. So which gives, if we equate d0 square or do square by 4 into square root of ps minus p, that is equal to dnx. I have used dnx into square root of p, assuming ct0 and ctn are almost equal. CTO are almost equal with CTN, which may not be there in practical situation, so we need to have a correction factor there. Now, if we take gauge pressure, so what is gauge pressure? Gauge pressure is the pressure with respect to the atmosphere. So that means we take the atmosphere pressure as 0 or the reference, taking PA equal to 0. Then P becomes supply pressure PS divided by 1 plus 16 into dn square x square by do to the power 4. So that way we can see that this way P is now in a nonlinearly related to x. To the displacement x. So the sensitivity when x is small, because it has square and in the denominator, so sensitivity will be large when displacement is small. So therefore, this can be a pneumatic displacement. Now, actually in a pneumatic system, what will happen? That this pressure signal will be tapped. This pressure signal will be tapped and will be transmitted as a feedback to a controller. So the pressure P, which is becoming proportional, not proportional, it is inversely proportional to the square with an offset, of course. So that would be transmitted in a feedback system. Therefore, in a pneumatic feedback system, this pressure P can be used as a quantity proportional to displacement. Not proportional. Quantity corresponding to displacement x. Okay, so we shall discuss a little bit on this feedback system tomorrow.